Okay, so today's class we'll solve a problem on shafts and then get to keys. Okay, so here's the problem. Okay, for the shaft shown below, the mating gears not shown. Drive the gears B and D. B is this one, and D is this one. So forces in the vertical direction as shown. Assume SUT is 100 kpsi, SY is 80 kpsi, SE is 24 kpsi. Compute the factor of safety, assuming static yielding using distortion energy, and factor of safety assuming fatigue failure, and D ASME elliptic criterion. So for this loading, there is a side view, the perspective and top, side views down. You're also given the radius of the pulleys at B and D, and you're going to compute the factor of safety. Now, what we can do is we can think of this in reverse. Let's see what the formula for factor of safety is based on the static yielding and fatigue failure criterion, and then figure out what we need in order to solve for those factor of safety, and then work our way backwards. So I'm going to pull up the factor of safety from the formulas we talked about last time. ASME elliptic. Okay, so let's see what is asked. Well, let's see what is needed in these formulas, and then what we know, and then what we need to compute in order to complete the calculation. So SE, SY, that's it. SE is known, SY is known, that's given. We need to know D, KF, KFS. Then we need to know TA, TM, MA, MM. That's it. Yeah, so those things are needed. Fill this up. SC is 24 kpsi, and SY is 80 kpsi. Okay, so we need to compute the remaining things. Now, remember that KF and KFS only appear if we suspect there's stress concentration or concentration due to fatigue. So this will only happen if there's a change in geometry. So this really depends on the geometry. And then D also really depends on where we think that the critical stress is, right? All these things are which need some notion of where the critical stress would be. If you look at the original problem over here, there are many places which you can suspect it to have high stresses. It could be the bearings, it could be the pulley of diameter D, it could be the pulley of diameter B, it could be the shaft. So we don't know. The only way we can figure that out is perhaps to compute what the torque is as a function of the length. We can also compute the moment as a function of length, right? So essentially what we're doing is we are trying to compute these things as a function of distance, and then make a case or figure out the critical location. That is the location where we have the maximum torque and maximum moment, which will then lead to high stress, and which will be the determining factor for the factor of safety. Okay, so we go back to what we've done in the past, which is drawing the free body diagram and evaluating torque, moment, shear force diagram, bending moment diagram, things like that. Okay, so let's do that. So here is a drawing. I'm going to just use this view. The first step is to draw a free body diagram. FBD. Okay, so in FBD here, we assume that it simply supported the bearings. So let's say there's a vertical reaction force here, a vertical reaction force here, VA, VE. So what we can do is we can compute VA and V because we need the shear force bending moment diagram. So let's do the summation. So this is the Y direction, this is the X direction. Summation of forces in the Y direction is equal to VA plus 2000 minus 6000 plus VE equals 0. So that gives me VA plus VE equals 4000. And then I can do moment about any point. Let's do it about point A. So if we do it point A, then we have 2000 acting at a distance of 1 inch. So that would be a moment in the counterclockwise, so positive. Then we have 6000 acting at a distance of 1, 1, and 1.5. 1 plus 1 plus 1.5 acting in the clockwise direction, so negative. And then VE. VE will act obviously positive counterclockwise, and so it will be a distance of 1 plus 1 plus 1.5 plus 1.5. So 1 plus 1 plus 1.5 plus 1.5. All this should be equal to 0. Okay, so V equals 6000 times 3.5 minus 2000 divided by 345. That's 3800 LBF. And then VA is 4000 minus 3800, just 200 LBF. Okay, so the first step, we've got VA and VE. Okay, now let's draw we need actually just two diagrams, bending moment diagram to give us M as a function of length, and we need the torque as a function of length. But somehow we can't just, let's just draw the shear force diagram, because with the shear force diagram, it's actually very easy to compute draw the bending moment diagram. So I'll make a copy of this. I'll need it. Let's take a copy of this. So SFD, PMD, and torque diagram. Okay, so for SFD, okay, so we know VA is 200, VE is 3800. So we start at E. That force is Just draw the y-axis. Okay, so 200 up, that remains constant till we reach point B, where there's a 2000 added to it, so it'll be 2200. So it's over here. It's flat till we go to point D, where we have to add, well, subtract 6000. So 2200 minus 6000. That will go down minus 3800. And then we stay at 3800 till we reach E, in which case it goes back to 0 because it's 3800 upwards. Okay, so that is our shear force diagram. Okay, let's draw the bending moment diagram. Okay, and what we'll do is we'll use the area under the curve to do this. So start at 0. These will be critical points. Okay. Okay, so we need a couple of things here. To draw this, we would need this length. This is 1 inch. This is 2.5 inches. 1 plus 1.5, and this is 1.5, I think. Okay, so this area is 200, so 200 times 1. This area is going to be 2200 times 2.5. It's 5500. And this area is minus 3800 times 1.5, which is equal to minus 5700. Okay, with that, we are ready to draw the shear force diagram. Starts with 0, goes to 200 at A. Then we need to add 5500 to 200, so that will be 5000. Yeah, so 5700. So it'll go linearly. Five, 700. Then we need to subtract 5700, so it will go down all the way. Okay, there is one more thing which I think is interesting, which is at C, we see there's a change in geometry. So we should look at the moment there, because of stress concentration, that could actually have a larger than a large moment, a bigger stress. So at C, which is 1 inch away, this point would be, so here the area is 2200 times 1, which is 2200. Okay, just this area. So we expect this to be 2400, because we need to add 2200 to 200, so 2400. Okay, so this is, let's put the points. So this is B, this is C, this is D, this is A, and this is E. Okay, so that's a very important diagram, the bending moment diagram. We are left with, if to draw one more diagram, that is the torque diagram. X. Okay, so how do we compute the torque? Well, we need to figure out what the torque is on the various elements. Now, the torque will be induced only due to the pulleys, because the pulleys right here, the pulleys are transmitting this force 2000 lb and 6000 lb. That will lead to a torque. So the torque, you can actually write it down here. The torque at B would be the force at B times the radius at B. So it'll be 2000 times 9, which is 18,000. Also, we have, similarly, we have torque at D is force at D times radius at D. So it's 6,000 times the radius is 3. So it's 18,000 lb lbf inch. Okay, so we got that. So now we can use this. So the torque is essentially 0 from A all the way to C. It ramps up to 18,000 in one direction, and then it remains constant, and it goes down to 0 again because there's 18,000 acting the other way. So the torque diagram will look like this. It will be 0 all the way to B, ramp up to 18,000, keep constant till we hit D, go down, it remains 0. Okay, so with those diagrams, we are in a position to figure out the critical location. Okay, so the critical locations are where the torque and the moment is maximum. Yeah.
Should the, for the moment, shouldn't that be 2200 at C?
Uh,
2200 times 1.
over here, you mean this point C? Yeah, it'll be 2200 at over here, but then you need to add this 200, right?
Oh,
Yeah. Same for here, 5,500. You need to add the 200 to get 5,700. Because it's basically this formula. It's m equals integral v dx. So and the limits are here the limit would be b to c. So the area from c minus b should, but the area under till b is 200. So you have to add that effectively. This will be, sorry, maybe I should write it this way. Hold on. Okay, so how do you get this? Well, we have integral dm equals integral v dx. So from b to c, b to c. So mc minus mb equals area under the curve, which is 2200, but mb is 200. So when you want to compute the moment at C, you need to move this 200 on the other side, and you get 2,400. Okay, so critical location. Okay, so we need to find a critical location as the location where the stresses are the maximum. There are only two candidates. There is one is, well, you can see that the torque is essentially the constant here, and then there is so the torque really anywhere between B, C, and D would have the same torque. So it just reduces to which point has the biggest moment. Now there are two candidates here. There is one candidate is D, right? Because the moment here is 5,700, and the other candidate is C. And why would C be a candidate? It's because there's a change in geometry at C, there's stress concentration, and the stress concentration can lead to it will lead to a KT, and that if the KT is high enough, then you would have high stresses at C. Okay, so there are two candidates. There are two possible locations, C and D. Both C and D have the same torque. So although C has a lower M than D, there is okay, D as shown in the bending moment diagram, there is a fillet at C which leads to a stress concentration at C. The actual moment at C would be Kf times moment at C. Is that true? Let's see. Oh, well, my bad. That's partially true. Uh, yeah, so this is the actual moment, but the stress at D would be something like uh, should be proportional to, it would be stress. This is the stress due to moment. So stress at D is md y divided by I, but we know I is pi d raised to 4 divided by 64, right? So you can get, doing that calculation, you get 32 md divided by pi d cube. The stress at C is sigma C equals 32. So this is diameter is D, and mc pi d kf should be here, and pi d at C cube. Okay, so what happens is when you do this calculation, that is, if you compute kf and then you put the diameter at C, which is, by the way, smaller than the diameter at, so you can see here the diameter at C is what, 2.5 inches, versus the diameter at capital D is 5 inches. So the stress, just because of the diameter, is since it's proportional to D cube, will be 8 times higher, because it'll be, it's 2.5 versus 5. So not only because of the kf, it's also because of the diameter, the stresses at C are going to be higher than D, because the diameter at C is 2.5 inch versus diameter at D is 5 inch. So the factor of 8 higher, but 8 times higher would mean that it'll go, well, it'll be 8 times 2,400. That's like way higher than 5,700. So it's clear that C is the critical point, not D. C is the critical location because of lower diameter at C and Kf, which is greater than 1. So both those factors will lead to C being the most important point. So we need to compute the stress at, well, we need to use point C to design or compute the factor of safety. That's what it boils down to. Okay, so we have C. So we have gone through this whole step process of computing C. Now we have to now, since we got the critical point, what we have to do is we need to go back and see what was needed. We said we need all these things, right? TA, TM, MA, MM, T, KF, KFS. I think we have answers to some of them. We know D is 2.5 inches because it's C. We'll do that calculations. Let's compute TA, TM, MA, MM. So at C, we have the moment. There are two moments, MM and MA. So if you go back here, we have computed M at C to be 2,400. Now, what we assume is that, well, it's true that this shaft is spinning continuously. So what we expect is that the stress sigma m is going to be cyclic. It's going to be vary between plus or minus. So the mean component of the stress is going to be 0, but the alternating part is going to be non-zero. It's actually going to be the same as what we computed there. It's what, 2,400. So we have mm is 0, and this is 2,400 because of the way this thing rotates. Then we have Tm and Ta. Now Tm is actually 18,000 because this torque is going to be constant. It's going to be the average stress, and the alternating part should be 0. So Tm is 18,000, and then Ta is 0. We also have computed D. The D is the location to, which is C. So D is DC, 0.5 inch. I think it's in this figure, 2.5 inch. Okay. So we've got all those things. We are only left with one more thing, and then we should be able to use the formula, which is we need to compute these factors, Kf, Kfs. Okay, so how to compute Kf, Kfs? We've done in the past. We need to first compute the stress concentration factor, Kt. Then we need to compute Q, and then we can compute Kf. So we'll do that. So first we'll get Kt. So what I did was you need to use these to compute Kt. So let's see what this is. So capital D. So we need ratios, capital D divided by small d, and we need R. We can get those from looking at point C. So point C, the larger diameter is 5, the smaller diameter is 2.5, and the radius is 3/16 of an inch. So capital D is 5 inch, small d is 2.5 inch, and the radius is 3/16 of an inch. So we need capital D divided by small d, so 5 divided by 2.5, which is 2. We need R divided by D, which is 3/16 divided by 2.5, which is 0.075. And now we can go and figure out these values. So for the first one, Kt, we need to go at ratio of 2. So that's right, this point, this curve, and then 0.075. 0.075 is right here. So we go up here. So it looks like it's between, it looks like it's slightly below 1.6. I just assumed a value of 1.58. And then here we have 0.075, and we need a ratio of 2. So unfortunately, we have 3 and we have 1.5. So we'll have to ballpark it. It should be somewhere. So anywhere between this and this point, I don't know, we can just make I guess, a guess here. It's here. Okay, this is just making a guess. This is 2, so it's a little below 2. I don't know, let's assume 1.9. So KT is 1.9 and KTS is 1.58. So that's what we got from these figures. Now we need to compute Q so that we can compute KF and KFS. Okay, so let's look at these figures. Now for these figures, we need the notch radius, which we know is 3/16 of an inch, which is, what's 3/16 of an inch? It is 0.1875. And then we need SUT. This is in the problem. SUT is given, it is 100 kpsi. Okay, now we can compute Q and QS. So 100 kpsi is here, and then 0.1875, it looks like it's off the chart. We just have 116. Okay, but what we can see here is that this line actually is asymptotic, so it sort of becomes flat. So it's fine to just assume this value, which is not exactly what we wanted. It's actually beyond that. 0.18 is probably over here or somewhere, but we'll assume that it just goes straight like this. So this point is maybe here, somewhere between a little less than 0.9. Let's just make it 0.85. So that is Q. Okay, next is QS. So this is 100, line 100. And then we need 0.187. Again, it's off the chart. 0.1875 is off the chart, but it asymptotes here. So you can just take this value, whatever it is. It is somewhere here. Maybe the same value. I assumed it's 0.9 QS. So QS is 0.9 and Q is 0.8. Okay, with that we can compute KF. It's 1 plus Q, KT minus 1, 1 plus Q. Q is 0.85. KT was computed in the last page. It was 1.9 minus 1. So that comes out to be 1.765. And KFS is 1 plus QS, KTS minus 1 equals 1 plus QS, which is computed to be 0.9. KTS was computed in the previous page. It was 1.58 minus 1. This comes out to be 1.522. Okay, we are all set. We have computed KF, KFS. Okay, the last step is to compute the factor of safety. Okay, so the first step is yield. So SY by sigma max. Sigma max is 16 divided by pi d cube, 4 times kf ma plus mm square plus 3 times kfs a plus tm square, and this whole thing raised to half. So a couple of things here are 0. Mm is 0 and Ta is 0. This is 16 times divided by pi times 2.5 cube. 4 times Kf is 1.765. Ma is 2, 4, 2400. This whole thing should be squared plus 3 times KFS was 1.522 was 18,000 square raised to half. It comes out to be 1.57 times 10 raised to 4 psi. And so to compute ny, we can put sy, which is 80 times 10 raised to 3 psi time divided by 1.57 times 10 raised to 4. It comes out to be 5.09.
Point five.
5 to this one,
Yeah.
1.522. Okay, and the next one, this is part A. Part B, again, there's a long formula. Part B, the formula is 1 divided by NF equals 16 pi d cube. Okay. 4 kf ma sc square plus 3 kfs dA divided by sy square plus, let me continue the next line, 4 kf sc square plus 3 kfs dm sy square is to half. Couple of things are 0. This one, this is 0, and this is 0. 1 divided by NF equals 16 pi d cube. Pi, let's just put in the value 2.5 cube, 4, 1.765 times 2400 divided by 24 times 10 raised to 3, the whole thing squared, plus 3 times KFS, so 1.522 times 18,000 divided by SY, which is 80 times 10 raised to 3, the whole thing raised to half. Okay, so this gives 1 divided by NF is 0.2257, and then the NF is 4.43. That's the answer.